So why do we do back titrations? There's a couple of main reasons. The first one is that it allows us to find a purity of solids, which are obviously difficult to titrate. And also sometimes the reaction is just too slow for a titration to happen. In order to find the endpoint, we need the reaction to be extremely fast. We can't wait 10 minutes after adding each drop to find out if the reaction has completed. So here we're going to do a worked example. You've been given some calcium carbonate, but it's been contaminated with calcium sulfate. How could you find the purity of that? Well, if you didn't want to use back titrations, you could take the solid, weigh it out, and drop by drop add a known concentration of HCl until you no longer observe bubbles. But that's going to be pretty difficult to determine exactly when you stop seeing bubbles as you add it drop by drop. So your accuracy is going to be pretty awful. So we can use back titrations to find a far more accurate method of determining the purity of calcium carbonate. The method that we're going to use, we're going to take 5 grams of our impure calcium carbonate, place it in a beaker, and initially add 50 centimeters cubed of 1 mole per decimeter cubed HCl. And we use a burette for that so that we can accurately record exactly how much acid we've added. Give the mixture a stir and let it stop fizzing. We then add a further 10 centimeters cubed of acid using the burette, and we note that although we've added our 10 centimeters cubed, actually no further fizzing has actually been observed. So we know that it actually all reacted after 50, but we've added a total of 60 just to make sure. We then take 25 centimeters cubed of that solution out using a pipette. So again, we can accurately record that and add that to a conical flask together with 3 drops of phenolphthalein indicator. And then we are going to do a titration using sodium hydroxide. That's going to be added to the burette, and the concentration of our sodium hydroxide is 0.500 moles per decimeter cubed. And after doing the various titrations, we come to the conclusion that we need 10.15 centimeters cubed of sodium hydroxide to reach the endpoint. So let's take that now step by step and draw conclusions at each point. So step 1, nice and easy. There's my beaker and I've added 5 grams of calcium carbonate to it. Here comes along my burette and I add 50 centimeters cubed of HCl to it. So I've now got a solution. It's fizzed, stopped fizzing. Add another 10 centimeters cubed and no further fizzing is observed. So now we can work out the total number of moles of HCl we've added, which is going to be our concentration, which is 1.00, times the total volume in decimeters cubed. So I need to convert my 60 to 0.6 decimeters cubed, and therefore total moles of HCl added at this stage is 0.06. So in step 2, we're going to take 25.0 centimeters cubed of that solution, remove it using a pipette. We're then going to place that in a conical flask and add 3 drops of our phenolphthalein indicator. And finally, we're going to use a solution of 0.500 moles per decimeter cubed sodium hydroxide, which will be added to burette, and we find that we require 10.15 centimeters cubed of sodium hydroxide to reach the endpoint. We can use this information to find the moles of sodium hydroxide that we have used during that titration. So moles of sodium hydroxide is going to be our concentration times volume. And remember, we need to convert our volume into decimeters cubed, and that tells us we have 0.005075 moles of sodium hydroxide that we added. We look at the equation, and it's a 1-to-1 reaction between HCl and sodium hydroxide. So we have the same number of moles of HCl in the 25 centimeters cubed that we added using our pipette. And so the moles of HCl in the original 60 centimeters cubed is going to be 0.01218 moles. It's now time to pull all the information together to find the percentage purity. So we know from the previous slides the total number of moles of HCl that we added at the beginning of the experiment, and we know the moles of HCl that remained after we reacted with the calcium carbonate, and that information was from the titration. So we can find the moles of HCl that reacted by just taking 0.01218 away from 0.0600 moles. That leaves us with 0.04782 moles of hydrochloric acid that react with the calcium carbonate. We then bring in the equation, and for every 2 moles of hydrochloric acid, I need 1 mole of calcium carbonate. So I can divide that by 2 to give me 0.02591 moles of calcium carbonate. Then it's relatively straightforward to convert that into a mass of calcium carbonate by timesing by the molar mass, which is 100.1. And finally, my percentage purity is going to be 2.59 divided by the 5 grams that we originally had times 100 to give me 51.9%. So that was a step-by-step work example of a back titration calculation, and we'll do a few more just so you can get the idea of this in future videos.